Hey everyone, in this video we are implementing a solution for problem 167, a two-sum 2. So we are given an array of integers, numbers, and this array is already sorted in non-descending order or increasing. And we are asked to find two numbers such that if we add those two numbers together, there will be equal to a target value that's given as a parameter in this function. So for example, here, if we take a look at this example, the numbers are already sorted increasing, and with a given target value of 9, there are exactly two values, 2 and 7, that if we add them together, it will be equal to 9. And it is guaranteed by the problem that there is exactly one solution, not 2 and not 0. One other constraint is that we shouldn't use extra memory, or we should only consume a constant memory in this implementation. So we cannot allocate new arrays or new lists in the implementation, and we should already use the numbers that it's already allocated. So this is something that we cannot use recursive functions, for example, because as we pass the values for the recursives, a new copy of the object would be created, and we cannot use them. So what we are going to do, we are going to implement a solution with O(n) log n. And this solution is that we know that the array is already sorted in increasing. And with we know we are looking for two numbers that be equal to a target. So we are iterating through each number here. So starting from the first one, and we know if the value of this cell is n, we should look, or we should find a target minus n, target minus n in this array. And since we know that the array is already sorted in non-descending order, we can use a binary search using that consume n log n of time. The time complexity of binary search is log n. So by binary search, we test if target minus n exists in the array or not. If so, we simply just return it and the solution is found. Otherwise, we move to the next one from this one, and then look for a target minus n again in the rest of the array. So at each iteration, since the number is increasing, you expect to see a target minus n be in the right hand side, because the number itself has already checked in the previous iterations. So for each iteration, we are just running a binary search on the rest of the array, and we are using the same array. We are not allocating a new array for our binary search, and we are just using indices, the start and end of the indices that indicates this at the right hand side portion of the whole array to run the binary search. So let's implement that. So as we discussed, we are going to use a binary search method. By default in Python, you can there is a binary search already implemented. It is built in, so you can import it using from bisect import bisect left as binary search. There are two versions, bisect left and bisect right, which just returns if there are equal values, should it return the left index or the first index, or the right index if there are repeated values or equal values. But in this case, we are not going to implement that. But the whole idea is that given a sorted array, whenever we are using for the target value x in this sorted array, we define two low and high values. So we can implement this function as well, but I'm going to use the built-in one. But the idea is that at each iteration, we just compute the average of low and high, or find the median in this array, and compare it with x. If x is less than the mid value, so we drop the right portion. Otherwise, we drop the left, and we repeat that again. So we shift the high to here, and then repeat that. Eventually, the array is shrinking in logarithmically, and in log n we can find the solution. So this is the just to show you that the documentation for the official documentation for bisect left or the binary search that we are going to use, as we discussed, there are the array. The parameters low, high here is to indicate which portion of the array we are going to look for a value that we are going to use that to indicate what portion to look for a value. But the implementation is the one that we discussed. So given two low and high values, while low is less than 1, it is always looking for a mid value and compare it with the target, and then if it found, simply return it, otherwise recalculate the low high values. So let's implement that for in enumerate numbers. The reason why I'm going to use n, so we could simply just iterate I or for n in numbers, but as the result of this solution, we should return two indices rather than the two numbers. So in this problem, for example, we should return the first number and the second number, the indices of the values, not the values themselves as the return value of this function. So I'm gonna use enumerate over this list so that we keep track of the index of each number. So what we are looking for is the target. So running binary search on the numbers. The target is the target value for the binary search is target minus n. This is the value, and here we can see the low value that in order to speed up the process, we already know that target minus n shouldn't be on the left hand side and it is on the right hand side. So I plus 1. So this is the j, or the index for the other number, if found. So what binary search returns if in an array, for example, 2, 5, and 9, looking for a 6, it is returning the index point, so that if we wanted to insert a value in that sorted array, so this is 5. If we are looking for a 6, it would return 2, indicating that we should insert 6 in index 2. But it doesn't return the index of the value itself, because we don't know if the value exists or not. If it was 269, it would return 1, so that indicating that we should return 6, the new value in this index. So we can find the index by bisect left, but instead of inserting a value into the array, use that as a method of checking if that index itself is equal to the one that we are looking for or not. So first of all, we should check if j is less than the length of the numbers, because for the same reason, it could be the value could be not found and go beyond the array. So if j is valid and numbers of j equal to the one that you are looking for, this is the number that we are looking for. If the index that binary search found is exactly equal to the target, so the problem is solved. We already found the indices. I and j are the indices that we are looking for, so we can simply return it. So binary search is not defined. Oh, the other criteria here is that as the return value of the indices for this function is looking for a one indexed or one based array, not zero based. So in Python, arrays are zero based, so we are iterating I and j from 0 to n minus 1, or the length of numbers minus 1. So we can simply add 1 here, and that's it. So let's submit that. So it is accepted. So we could solve this problem in O n log n using the default implementation of binary search in Python. But if you're looking for a implementation, I would put the link of the binary search implementation, so you can simply just copy paste this function in the solution, or just read this code to understand the logic of binary search. but otherwise that's everything for this problem.